Welcome to the Arithmetic Zone, and welcome to another AP Physics tutorial. This time we're going to look at a problem involving an Atwood machine when the pulley has mass. So we have our little Atwood machine set up to the right, and now let's read this problem. The pulley shown has a moment of inertia of 5 kilograms times meters squared and a radius of 0.5 meter. The cord supporting the masses M1 and M2 does not slip, and the axle is frictionless. So essentially, it's giving us some quantities, but note that it gives us the moment of inertia of the pulley and a radius for the pulley. So when they give you these values, what that means is that it's basically telling you that this system is an Atwood machine, but the pulley actually has mass. And when the pulley has mass, you're going to have to account for the effect that the pulley has on the acceleration and the tension in the system. So we were given that the moment of inertia of the pulley itself is 5 kilograms times meters squared. So that means that this pulley is rotating, which, that does make sense because that is how a pulley works. And we were also given that the radius is 0.5 meters. So essentially this distance, like from the center to the edge, that would be 0.5 meters. Now let's look at the steps that I would take whenever I'm given a problem like this. So first step would be to draw a free body diagram for both the masses and the pulley. So let's do that. So for M1, so I'm just going to label this M1. We obviously know that it's being acted on by gravity, which we're going to call it M1G, because, gravitational force is equal to the mass times the gravitational constant. But there is also a tension force because it's being attached to a rope. And we're just going to, oh God, that looks really bad. Let me just erase that. So we know that it's also being attached to a cord, which means that there is going to be a tension force up. So that's M1. Now M2 is going to be much of the same. So we're going to draw another block with the center of mass, and gravitational force again is mg, so m2g, and then we have another tension force. We're going to call it T2. And now we want to draw the free body diagram for the pulley. Now the pulley is a little different because, well, the pulley is not, this block. It's this little cylinder. So we're going to draw a circle. Center of mass would be in the centroid right here. And this centroid does actually experience its own gravitational force because, all gravitational forces act on the center of mass. So we could just draw an arrow straight down, call it MPG. But this isn't very relevant to the system. This force isn't going to do anything for the direction or acceleration or tension of the system. But what we do care about is the tension of the cords. So notice how, this pulley is being attached to two cords on the edges like that. And we have tension forces. So what that means is that there's going to be a force, going down, T1, and another force going down right here, T2. And these are the contact forces, because ultimately, when you have a force that's outside of the center of mass like this, and it acts on the object like that, a torque is occurring on this object, and when a torque occurs, the object's going to spin. And even though these torques are both occurring down, they're actually going to spin this pulley in opposite directions. Think about it. If you were to spin something downward from the left side, it's going to spin this way, which is counterclockwise. But if you were to spin an object down from the right side, it's going to spin this way, clockwise. So it's actually going to spin in two opposite directions. It's happening at the same time, but we're going to see that one of these tension forces is stronger than the other. Hence, it's going to accelerate toward one direction. But we need more information before we can determine that. And luckily we get that information right now. So part B, find the acceleration of each mass when m1 is equal to 2 kilograms and m2 is equal to 5 kilograms. So what it's saying is m2 is heavier than m1. And I really wished I kept the Atwood machine drawing, but to give you a poor man's version of it, I'm just gonna draw it right now. So this is m2 and this is m1. m2 has a greater mass than m1, and because m2 has a greater mass than m1, this pulley is going to be spinning this way, which means that this tension force is going to be stronger. Hence, the whole system is going to accelerate clockwise. And when we're dealing with rotational motion, clockwise is negative and counterclockwise is positive. So that's how we're going to keep it when we're solving for the acceleration. Now, finding the acceleration is a very long process. There are multiple ways to do this, but I'm going to do it in the way I prefer. So what's an equation to relate our given quantities plus acceleration plus the torque? Well, we have torque is equal to the moment of inertia times angular acceleration. But it's not just any torque, it's the net torque, or the sum of the torques. And as we saw before, there were two torques acting on this pulley, both pointing down. So let's call them torque 1 plus torque 2 is equal to I alpha. And now we want to solve and evaluate these two torque values. So let's start with the first torque, torque 1. And let me just again redraw the pulley. We said that the torques were acting like this with through the tension forces, so T1 and T2. Anyway, torque 1, if you don't remember the equation for torque, you might know it as T is equal to Fr, but it's also important to keep in mind that that's just one part of it, or rather two parts. Torque is equal to the multiplication of the force that's causing the torque, the radius, and the distance by theta between the force and the radius. So we're going to express that in an angle. So torque 1 is going to be equal to F1 times R times sine of 90 degrees. Why is it 90 degrees? Well, let's see. So torque 1, the force that's causing the torque is tension 1, so T1. And then, T1 is pointing down, and the radius R is 0.5. And this is the radius, and you see how it forms like a 90-degree angle? It's perpendicular, hence we use 90 degrees, and sine of 90 degrees is just 1, so we can just cancel that out. And that's usually why you see it expressed as T is equal to Fr, because more often than not, the torque and the radius are going to be perpendicular, but sometimes they're not, and then that's when you have to account for the angle. So we have that T1, or torque 1 is equal to the tension 1 times radius, and we said the radius was 0.5 meters. Now, unfortunately, we don't really know anything beyond this point, so we're going to have to leave it as torque 1 is equal to 0.5 T1. Now we're going to do the same thing for torque 2. So let me just erase that. Torque 2 is going to be equal to force 2 times the radius times sine of 90 degrees, because again, this torque is perpendicular to the radius, so it's going to be a 90-degree angle, and we know that sine of 90 degrees is just 1. I hope you guys have been watching that unit circle series. Now, it's important to realize that even though this force is also pointing down, I did say that it's going to cause the pulley to spin in an opposite direction. It's going to cause it to spin clockwise. And when we're dealing with clockwise motion, we're going to express that as a negative quantity. Hence, torque 2 is going to be equal to negative T2 times the 0.5 meters. So torque 2 is equal to negative 0.5 T2. You might be thinking, well, what did that even accomplish? You know, I did all that work. Like, what did that even do? Well, we can go back to our original equation. Torque 1 plus torque 2 is equal to I alpha, and that we can now plug this in. So 0.5 times tension 1 minus 0.5 times tension 2 is equal to I alpha. Now we have to determine the quantity of these tensions. Or rather, we gotta express the tension forces in quantities that we actually know. How do we do that? Well, remember those free body diagrams we made? Well, we're gonna use those. So we're gonna do this process for both of the masses, and we're gonna essentially use Newton's second law. So let's say F net 1 is equal to M1 times A. And we saw in our first free body diagram that the tension force was up, the gravity was down. And I'm just going to redraw that. So, you know, this is T1. This is M1G. Now, the question is, which one's positive, which one's negative? Well, the positive quantity is the one that's in the same direction as the acceleration. And notice the acceleration is this way. It's going clockwise. So what direction is that? When we look at our diagram, tension. So tension is going to be the positive quantity. So we're going to have T1 minus M1G is equal to M1A. And we were told that M1 is equal to 2 kilograms. And by approximating the value of G to 10 meters per second squared, we can set this whole equation up so that T1 is equal to 2A plus 20. And now for the second mass, so F net 2 is equal to M2A. Again, let me draw the free body diagram. So, you know, this is T2, this is M2G. Even though the arrows, like on our screen, you know, are pointing in the same direction, the tensions are both up, the gravity's both down, you know, we got to relate it to the direction of the acceleration. Acceleration is going clockwise this way. So, what's the same direction as this acceleration? It's the gravity. Hence, gravitational force is going to be positive in our case. So M2G minus T2 is equal to M2A. And knowing that M2 is equal to 5 kilograms, and again, substituting in 10 meters per second squared for G, we get that T2 is equal to 50 minus 5A. So we did a lot of work here, but we're still not done. We got to find the linear acceleration. But luckily, we expressed the tension in terms of linear acceleration. But in our main equation right here, we still have angular acceleration. So how are we going to get rid of that angular acceleration? Well, what's angular acceleration equal to? Angular acceleration is equal to a over r, with r being the radius. So now we're going to rewrite this whole expression, substituting in t1 for this value, t2 for that value, and alpha for a over r. We're going to have I times a over r is equal to half. I'm just going to write the fraction so I can save space. 2a plus 20 minus half of 50 minus 5a. And I apologize for how bad this looks. So, do you guys remember what the value of I was? It was told in the very beginning of the question. So, by knowing the quantity of I as 5 kilograms times meters squared, let's apply it into this equation. So, 5 kilograms times meters squared. times the linear acceleration a over r, which is 0.5 meters, and is equal to, so we're going to distribute this half, so this becomes a plus 10, and if we distribute this negative half to here, this becomes minus 25 plus 2.5a. So, when we're dividing 5 by 0.5, it doubles, so we have 10a, and then if we combine like terms right here, we have 10a is equal to 3.5a minus 15. And then if we just subtract this 3.5a over, and then after that you just divide, you should get that the linear acceleration, which for this whole system, a is equal to negative 2.308 meters per second squared. Don't worry if your decimals aren't exact, but if it's negative 2.3, then I'd say that's good enough, and that is the acceleration of the whole system. It's accelerating this way at 2.308 meters per second squared. And note that it is a negative number, which makes sense because the acceleration again is going clockwise, and clockwise is represented with a negative number. So that's a lot of work just for the linear acceleration, but fortunately we still have another question to answer. So part C, find the tension in the cable supporting M1 and the tension in the cable supporting M2. Luckily, we just found the linear acceleration, and we already expressed the tension in terms of the acceleration, so this is very easy. We said that T1 was equal to 2a plus 20. So it's really all just a matter of substituting at this point. So T1 is equal to 2 times negative 2.308 meters per second squared plus 20. Make sure you do keep that negative there, as the direction is important, and you get that the tension is equal to 15.385 Newton. And now for the second tension force, the one with M2, we said that T2 is equal to 50 minus 5a. So T2 is equal to 50 minus 5 times negative 2.308 meters per second squared, and you really cannot see that decimal point there. So negative 2.308 meters per second squared. These two negatives, they're going to both become positive, and we're going to get a large tension force for T2. 61.538 newtons. So this tension, the second tension force, the one with M2, is higher than the first tension force, T1, and that should make sense. Anyway, that's gonna be the end of this video. I teased this tutorial a long while back in the trailer, but I'm glad that I was finally able to give you guys all the videos that I planned to release in the future by that point. And we have many more videos that I plan to release, specifically with math and of course the Simple Java series. I don't have any more plans with the bonus tutorials, not right now. Who knows what's gonna happen, but I'll see you guys next week.